So there's been just published a very exciting paper using data from NASA's Curiosity rover on Mars to help explain what Curiosity found. We have with us Nina Lanza and lead author Patrick Gasd, both from Los Alamos National Labs. So how are you doing, guys?
Well, great. I'm feeling pretty excited right now. I just got off of a training session. I'm working on doing some analog activities for Artemis, which of course is the next human mission to the moon. And our crew, who's going to be working with us next week, is super excited. And I was even more excited after hearing their enthusiasm. So I'm really looking forward to the next week. And of course, there's so much going on right now in space exploration. It's a great time to be a planetary scientist.
And how are you doing, Patrick?
Doing great.
Okay. Well, let's talk about what you've actually found. So, is it right? You said you found elevated levels of a chemical called manganese oxide. Is that right? And what is this chemical? And what does it have to say about the early environment of Mars?
Yeah, so manganese oxide, it's a type of manganese mineral. There's actually a variety of different manganese oxides, but generally speaking, it means that you very likely had oxidizing conditions on the surface of Mars when it was deposited. And that's kind of a mystery. We don't really quite understand why there's, highly oxidizing conditions on the surface. We kind of know that Mars is a mostly CO2 rich atmosphere. So where is this oxygen? If that's the oxygen, where is that coming from? We have a lot of evidence from like the early Earth, which we kind of use as an analog here, that the early Earth didn't have much manganese oxide on the surface either. So we only got manganese depositing on the early Earth due to photosynthetic life. So that's a little bit strange for Mars because we don't have evidence for life on Mars. So where is all this oxygen coming from?
Right. So, Nina, you've you suggested in the paper sort of several mechanisms for where these elevated levels of manganese oxide could be coming from. Can you explain what are these mechanisms? How could it be there on Mars?
Well, exactly. So the big question, as Patrick just pointed out, how do we get this on Mars, given what we know about the environments today and what we think the environments were like in the past? The thing about manganese oxide minerals, as a family, they really need two things. They need a lot of liquid water, and they need some kind of a strong oxidant. And so already that tells us we've got to be in an environment on Mars that had a lot of water. Now, as you know, we are landing here in Gale Crater. We know from a lot of other lines of evidence that this used to host a lake. And this lake was long lasting. It was long lasting fresh water. And so we know that there was a lot of water there. But what about this oxidant? And it's still pretty mysterious. There are a lot of different options. But where we find this manganese in the context of the rocks that Patrick was talking about is something that looks like a shoreline. And Patrick can tell you a lot more about the very detailed measurements that he made. But when you're at a shoreline on Earth, at a lake, this is a place where you have a lot of interfaces between the atmosphere and the water, between groundwater and the lake waters. And this can provide you with so-called redox gradients. So redox is short for reduction, oxidation. So when you think about that, you can think about, we like to talk about things being rusty. That's oxidation from the Earth's atmosphere because we have oxygen in it. This is something that's very common on Earth, so that if you have a lake and you're right by the edge of the lake, the water is shallow and you've got a lot of churn in that water, and you can actually put oxygen into the water and do some really cool chemistry that can actually precipitate out minerals like manganese oxides. But where did that oxygen come from? That's the great question, and we don't have an answer for that. Now, other workers have suggested other potential oxidants that could have done this. Oxygen is the most famous oxidant. It's not the only one. The problem with these other oxidants, of course, is that they haven't been observed, or they haven't been observed in any kind of abundance. And so the question remains, could they have been there in the past and left no trace? It's hard to say. And of course, we don't have a time machine. We have these rocks. So this idea of where is that oxidant, it opens up some incredibly interesting questions that we don't necessarily have the answers to with this work, but it tells us there were very strong oxidants present on Mars at this time. What they were remains to be seen.
So, am I right to say that oxygen is kind of unstable in Earth's atmosphere? That you need something like life or something else to replenish it? Is that right, Patrick?
Yes, I mean, typically the way that we make oxygen on Earth is because there's trees and plant, algae and cyanobacteria everywhere that produce oxygen from CO2 from photosynthesis. And photosynthesis is kind of a new, somewhat more novel thing that life develops like about 2 billion years ago. And if you think about it, like life began like almost 4 billion years ago. So it's kind of new, And then on Mars, this was all 3.5 billion years ago when this was all deposited. So um, it's yeah, that's where this mystery would come in. It's like, okay, how does this oxygen get there? Is there some abiotic process, so a process that doesn't involve life that we don't understand about Mars right now?
Right. So maybe we can sort of discuss like the big question, obviously, which is, could this be from life? I mean, obviously, there's like that's the exciting explanation, and I'm sure we'd all want that to be true. And then there's the less exciting explanation. Maybe it's something abiotic. What are the possibilities here?
So, we discussed this a lot in the paper, but there's a few other microbes. There are microbes that um, don't produce oxygen, but um, they eat other chemicals, and then they can oxidize manganese as a consequence. But again, that points back to this life questions. Like we know that there's plenty of places on Earth where you can make manganese oxides. Either they involve photosynthetic life or they involve microbes sort of doing that redox reaction for us, and that's a very efficient process. And if we don't have that on Mars, and we have no evidence for that on Mars, of course, that means some other abiotic process is occurring. We just don't know what it is.
Right. Nina, what are your thoughts? Like, how excited should we be about this discovery? Is it possible biosignature, or could it be some other process? Or obviously it could be, but I mean, what are the chances?
Well, I don't know if I'm not going to bet on this because Mars is a different planet, but I think it is extremely exciting. I mean, there are a lot of questions that have been raised that we really can't answer with the data sets that we have. And that's why these types of materials, manganese rich materials, are an incredibly good target for sample return because without our laboratory measurements, we really wouldn't be able to differentiate between abiotic and biotic manganese. It's a very difficult problem even on Earth. But I will say that based on our understanding of Earth as a planet, this this type of material is incredibly intertwined with life on Earth, both directly and indirectly. As Patrick mentioned, there are many microbes that metabolize manganese in a variety of different ways. They can oxidize it, they can reduce it, they can produce it, they can eat it. There's a lot of things they can do because it's a redox sensitive element. But it also didn't show up in any kind of a large amount on Earth until after the rise of photosynthesis, after there was enough of an oxidant in the atmosphere. So there was life on Earth before photosynthesis, but there wasn't oxygen in the atmosphere. And in fact, that great oxygenation event totally transformed our planet and really changed what kind of mineralogy is possible. And so when we look at Mars as a planetary system, our best guide is Earth. It's not the same planet. So we can say there may be things happening on Mars that don't happen on Earth, but I do think it's prudent to look closely at our own planet, especially given the similarities between Earth and Mars. So this is my long-winded way of saying I think it's a really exciting finding, and especially looking, we see this manganese showing up in this nearshore lake environment. It's so classic on Earth, and it's a place that is extremely habitable and on Earth is inhabited. So to me, this is just lining up the pieces, just telling us the story. Manganese may be giving us insight into these ancient environments on Mars that we didn't know anything about. So whether or not life made it, I'm not sure. I think we have to be conservative and say, let's find the abiologic ways this can happen, because that will also tell us something about using this as a biosignature on Earth for ancient Earth rocks. All that being said, I am really excited about it. And it's one of those materials that I can't wait to get back into our laboratories to study more closely.
Right. Actually, I just want to check then. I mean, Patrick, it just occurred to me that would it be correct to say we are sure that Mars was habitable, but we are not sure it was habited? Is that a fair statement?
Yes, that's a perfect way to describe it. It was. We have a lot of evidence that Mars was habitable, but inhabited, we don't know. The next
Right.
mission, the Perseverance mission, which is there right now, is intended to look for signs of life and then return those samples in this Mars sample return that we just talked about. And then we would have the samples in the lab and we can analyze them with all the, you know, various really high-tech instruments we have in the lab and then try to look for that life.
Right. Well, actually, before we get onto that Mars sample return, I just want to know, like, Nina, as I understand it, are you the lead investigator for the ChemCam technology that actually was used by the rover to make these measurements? How does this thing work? Can you explain?
Sure, yeah. So the ChemCam instrument is actually a name that's short for chemistry and camera. So as you might imagine, we are both a camera and also a chemistry instrument. So we're located on the top of the mast. So we're like the head of the rover, and we've got this one left eye, a little cyclops eye. That's our telescope that actually collects light. Our main technique that we use is something called laser-induced breakdown spectroscopy, or LIBS, L-I-B-S. And how this works is that we focus a laser at a distance from the rover. It can be actually up to 7 meters or 23 feet away, so we don't have to touch the sample. We focus this laser on there and we actually heat up the sample so much that it vaporizes a little bit of material. It's actually hotter than the surface of the sun for a little bit, but only in a little tiny spot. It's about half a millimeter in diameter. And so we've excited these target atoms to higher electronic states. And as it cools, they will emit photons at characteristic wavelengths. So what that means is basically we can look at the color of light that this vapor makes, and we can figure out what elements are in the rock. And we don't have to touch the rock at all. We can see this at a distance. And so along with this chemistry technique, we can also take beautiful high resolution images so we can see exactly where we analyzed on that rock. And so we use, our camera is called a remote micro imager, or RMI. And so we can actually see little holes that we burn into the rock. So we can tell the difference between a light grain in a dark matrix, for example. So we can get very fine grain, high resolution chemistry data. We can also average that all together and get a bulk composition as well. And one of the things I love that we can do, we can also get a depth profile of composition. So every time we pulse that laser, it ablates a little more material. So we dig a little hole. And each time we do that, we can see the difference in that composition. So we can look at things like thin layers or rock coatings. And then we can also, if that weren't enough, we could also use our spectrometers in a passive mode. We can just open up the spectrometers, use reflected sunlight, and take a look at what those rocks look like in the very near infrared. And that can actually tell us something about mineralogy, which is sort of, well, how are these elements arranged in minerals? So really, ChemCam is an incredibly versatile tool. And we've done, at this point, almost 1 million shots on Mars, which is a lot of data. Certainly, we've looked at everything, but I think there are a lot of discoveries that actually are awaiting us as we dig deeper into those 1 million shots.
Well, so let's look forward to the future. Patrick, you mentioned sample return. What are the I mean, this is really cool technology as it stands. But what is on the horizon? How can we push further to answer these big questions about whether there was life on Mars?
This is the Perseverance rover mission. This is the mission that's been on the surface for a few years. They're exploring Jezero crater, which is a place where we believe that there was also a lake for some time. And then the idea is that it has this, again, it's the same sort of rover, has a mast, it has the SuperCam instrument, so it's like slightly more advanced than ChemCam. It has some more techniques. At the end of the arm of that rover, they have a drill core sampler, so they can take these cores that are like this big, like the size of a chapstick, essentially. And then they're going to try to cache these samples from these different parts of this lake. And then a later mission will go pick those up and bring them back to Earth. And then looking into the far future, of course, as Mars scientists, we would love to know like what NASA's thinking about for the next missions to Mars, or we could propose new missions to Mars. I personally would like to go explore a Mars cave. Caves are very interesting environments on the Earth. They can preserve very special environments. For example, ice can be stable in a cave for a very long time, and ice and water and rock interfaces are very interesting for these astrobiology reasons. And then also, the great thing about caves is that they're protected from the radiation environment impinging on the surface, and that's always been part of the reason why it's very hard to find organics on the surface, because they get broken down by the extreme radiation. So,
Right.
Nina, do you want to add anything?
Nina, go ahead.
Maybe I'll jump in. So I'm so glad you brought that up, Patrick, because just bringing it back to manganese, this is one of the things that manganese can actually do for microbes. You tend to see this adaptation in microbes that live in high UV environments on Earth, because manganese is like this natural, I will call it a sunscreen for microbes. So you can actually use that to protect yourself if you are in a near surface desert environment, like we see, on many places on Earth, but also that exists on Mars. So the Mars environment is not very friendly on the surface, but elements like manganese can actually be an adaptation to help protect microbes from those harsh radiation environments.
I remember I went to an ice cave in Iceland, and I remember someone saying that there were actually microbes inside the ice, like alive. I couldn't believe it. Is that right? And could there be something like that on Mars?
Yeah, I mean, Mars, there are caves on Mars that have been mapped. And then on top of that, these, like I said, the ice can be stable underground for a very long time um, because you have this kind of air pocket that's trapped in the cave. It has a certain different humidity and different temperatures, which can help ice be stable for a long time. And you mentioned ice cave in Iceland, but actually New Mexico, which most people would say is a pretty warm place. Well, there's permanent ice caves in New Mexico, so that kind of shows you that um, the caves can kind of give you these isolated pockets of environments that are specialized. And then if you have microbes that can evolve and live in them, they could be persistent for a long time. So,
Right. Nina, did you want to add something?
Sure. Well, I think what's really important to keep in mind when we think about life in these extreme environments, such as ice, which I think we can all agree is pretty extreme, is that it's really about the interfaces that are available. And in those interfaces, that is where the energy and the opportunity arises. So I think I'm not an expert in, ice microbes, but my understanding is that they require some of that very fine melt. So they need water. They're not frozen. They're actually living in little melty pockets. And again, that's the interface between the ice and, not ice, that is giving them an opportunity. They need the water to live. They need the ice to protect themselves, right? And so it's this very delicate knife edge there. So really, when we look for life and on other places and other planets where the environments are more extreme, we want to look for those interfaces. Where are the places where opportunities arises? That can be, in ice and where near melt is. That could be in the near surface of rocks, where you're not on the surface, but you're actually near the surface, where you can have access to atmospheric resources like, moisture, airfall, dust, but also be protected from the radiation environment. It's that. So when we are looking, that's why caves are such a great place. They represent a kind of a liminal space on the surface of Mars. And so it's a great place to be looking for life. And so it's not just ice, but it's really the total package of the environment.
Right. Okay, so just for a bit of fun at the end, I know we shouldn't do this scientifically, but if I gave you 50-50 odds and I said, right, look, here's $10. Which way are you going to bet? Was there life on Mars or wasn't there? Nina?
Well, it depends on the question you're asking. I know I'm being an annoying scientist here. It depends. But, is the question, was there life on Mars in the
Yeah.
past, or is there life on Mars now? And
No,
so,
was there? Let's go with was there.
So if you're asking me to say, is there, if there's a 50-50 chance, was there ancient life on Mars? I think I would say yes. Let's not say that I have, of course, said we've discovered that, but I think that given what we understand about chemistry and about the evolution of Earth and Mars as planets, I don't see why it wouldn't have arisen. And if it didn't, that's a hugely, profoundly important result.
And Patrick?
Oh yeah, I totally agree. I would take that bet any day that ancient life very likely would have been on Mars. I mean, Earth and Mars, again, ancient Earth and ancient Mars were very similar to each other. So, and they would have had all the same ingredients for life. So it's kind of, I've always said it's actually quite weird that we haven't found life on Mars yet because it should be there. But it's almost certainly a fossil at this point, right? It's very unlikely that we'll find life currently living on Mars unless we dig very deep underground, potentially in aquifers if they exist. But that's all very speculative.
Right. Well, luckily for us, we don't have to make these bets. That's a bit of fun. We can wait for data and see what the data brings us. In the meantime, thank you so much, Nina and Patrick.